You may have heard it said about Java or various other languages that, quote, everything is an object. And then often people kind of have to back down from that and say, well, there are some primitives which aren't objects or things like that. What we will find in Python is that that statement, that everything is an object, is actually very true for quite a lot of things that you might not even expect it to be true of. And the model for how things are handled as objects is a bit different than you might have encountered in other languages too. So to design a class in Python can be very simple. You need to state class and then the name of the class and a colon, and everything that belongs to the body of the class is going to be indented from there onward. And then you can define functions for it. You can define instance variables and class variables, and we'll get into a little later how exactly you do that. So here I've defined a class that does nothing. Not the most exciting or interesting class, but it's very simple to define. Its name is nothing. We define one function that's called do nothing. You'll notice that function takes a special variable called self, which we will get into later, but that's what allows you to call something like n dot do nothing. The n dot is defined by the function having the self parameter there. And then pass, which is just a no-op, do-nothing kind of statement. So pass is just a built-in Python statement that says, this is a line of code, it does nothing. So then down below, I create an n variable simply by saying n equals. And what does it equal? Well, it equals a new instance of nothing. And there is, you will see here, by the way, no constructor defined. Everybody gets a free default constructor, and that's what we're using here. And then we call n dot do nothing, which will simply do the pass here and do nothing. So this is all valid Python. Not very interesting. We could put like a print statement in here to confirm that it's actually validly calling to that do nothing or something, but then it would be a bit of a bad name for it, wouldn't it? So when I tell you that everything is an object in a pretty true sense in Python, it's going pretty far. Here I've defined an integer, and there's actually a class backing integers, and it has a constructor. That constructor by default constructs an integer with the value 0. And so here I've created an integer variable simply by saying I equals int. I could have said I equals 0, and it would similarly create an integer object that I can use in the background. It would take the 0 statement and create an integer object to point to for that. And I can create a new string. There's a constructor for the string class, str, with parentheses, and you give it some parameters, something that can be converted to a string. We'll see later how we make a class convertible to strings. And this one, if I fed it I, would be the string, quote, 0, end quote. I can even take a variable like I, and I can do I dot stuff. There are various functions that I could call. Usually for integers, we're just going to do typical, mathematical expressions or use them as an index to a list or things like that. But I could do I dot and then a function name and call to functions that belong to integer. There aren't many that are interesting for that, but this is different than, say, Java or C++, where integers are a primitive special type that I can't use the dot operator with. In Python, I technically can. Not much interesting to do that way, but I can. So even more so, everything is an object, or in other words, everything is backed by some class. And we're going to learn a little more about what a class actually boils down to in Python as we proceed forward. When you define methods or functions, there are no keywords that you have to use for static functions. And along with that, there is no automatic this kind of variable like you get in Java or C++. You provide a parameter called self as the first parameter to a function if you want that function to be non-static, if you want it to be an instance sort of function. For instance, the foo down here, it takes self and then some argument. And then it does some work with an instance variable, which we're using there by referencing self dot and that variable. And then it prints out the argument potentially. And then here is a static one that does not have the self. So if we want a static function, all we do is we just don't define the self parameter. Many beginning programmers in Python will just forget to include the self and accidentally make a static function. And the error messages you get in relation to this will often be confusing because to Python, what happens if you called little a dot foo static, for example, is it gets an extra parameter, more than it thinks it should get. Foo static only takes one parameter. And so it should only get that string, and you do that by calling using the class name. If you call and you expect it to be a non-static when it's actually been defined as static, you're going to get complaints that it takes too many parameters. If you forget to include, or if you include self and then you call it using the class, you're going to get complaints that you've given too few parameters. And so Python doesn't tell you you tried to call a static method non-statically or vice versa. It complains about the number of parameters because self is just a parameter here. So down below, I've created an a object that's called lowercase a. I call the non-static function by calling lowercase a dot foo, and I give it a string. And I call the static one by using the class name capital A dot foo static, and I give it a string. So these parts are done implicitly, and it can be very easy to make mistakes and create a static function when you meant to create a non-static one, or vice versa. Variables for a class are somewhat similar in this relationship with self or not using self, and we'll see a little more on that later. But for an instance variable, you use them and define them in functions that have the self reference, in non-static functions. You don't have to declare instance variables in advance, but if you're not careful to make sure that they are declared before you go to use them, then your program will encounter errors and say that that variable is not yet defined. For instance, this class looks good. It's got a set name and a get name, but it makes no guarantee that self.name will have a value before getName is called, and that's exactly what happens here. I say a equals a new a, which calls to that automatically defined no parameter constructor, which doesn't define any instance variables or anything for me. And then I call a.getName, which tries to get self.name, but self has no name at this point. If I had called setName first, that would be fine, but this is not the best of designs. The better design would be to define my own constructor and to make sure that self.name started out with some value, and we'll see an example of that on the next slide. It's worth noting that variables are just accessible. A user of our code, whether they're using it as a library or they have our code files and they're able to modify them, they're going to be able to mess with those variables and they can just reference them. So you could say a.name. There's no setting it private. There is a convention in Python that if a variable has the name underscore and then the variable name, that it should be left alone and it should be treated as private. And this is particularly important to do if you did something special, like guaranteeing that name could never be the empty string, or guaranteeing that some count variable could never be negative, or things like that. And you don't want people who use your code to change it and violate that guarantee that you've intended to set up. Then you give it the underscore before its name, and that indicates conventionally that it shouldn't be modified. There is another way to make variables accessible and look functional while still having some control over what's done with them. And I'll show you a little bit of that here. First off, I want to point out that I've defined a constructor in this class. The constructor is a special function. It does not have the same name as the class when you define it. When you define it with 2 underscores and then init, I-N-I-T, and then 2 more underscores. And it must take self as its first parameter. Of course, it cannot be static. You can't have a static constructor. And then it could take more arguments if we wanted it to take more arguments. And so here I've defined an init that will take no arguments except self, which means that when I call capital A, to create or to call a constructor with no parameters, this init here, init self, is what will get called. So now my class is a little safer because I say self.name equals empty string. So if someone were to try to get name before setName was called, they would get the empty string as their name by default. We could have defined another constructor that takes a name parameter as well. That would be fine too. But the real lesson that I want you to take away from this slide is that I've actually created a structure that will help to make a little more of an interface for people to use my class in a more natural way. And again, remember that Python philosophy is that there should be one obvious way to do things. I don't really want a user to have to guess at what the rules are for names in my class. So I do 2 things here. I define an underscore name variable that indicates to people that are using my code as a library, this is private. You really shouldn't mess with this. And then I define a property that's just called name with no underscore that they can use as a variable to interface with my class. Here's what we do. We define a set, a get, and a delete, or sort of an unset. It turns it back to whatever should be the sort of empty or unused version of the thing. And we try to define these so that they are safe. So if, for example, I wanted to make sure that names always start with a capital letter, then I could write in setName, if the name they've given to me as a parameter does not have a capital letter as its first character, then change the first character to be an uppercase letter, and then store it in underscore name. So underscore name is my private way to store the actual name. And then they pass me in whatever they pass me, and I make sure it follows my rules. I make sure that it's valid for whatever the situation is. Another example of this would be if I were writing a video game and there were boundaries that the characters couldn't go outside of. If someone called to move a character and they were going to move outside of one of those boundaries, then I could have my set position sort of function to limit and pull them back inside the boundaries so that they never actually got out of the screen space or something like that. So when you define a property like this, all you need is 3 functions, a get, a set, and a delete. And then you give a description for it as well, for documentation purposes and things like that. And then you say what name you want it to, or what variable name you want it to behave as. Here, name equals the property get name, set name, delete name with the description object's name. And then I call A equals capital A constructor, which will call to init. That's just how those names sort of are matched up is when you ask to construct, it will find the init that matches that signature. For instance, one that takes only self here. Then I can say a.name equals test. This will call to set name, and it will store that name that was passed in underscore name. And again, I could do some verification to this, make sure that it has no punctuation in it, strip away any extra spaces on the ends, whatever things I wanted to do to make sure that names fit the right format. I could do that in set name. And the user would see no difference, except for when they went to ask for the name, they would get back the name that followed whatever conventions I had written in set name to make sure that names were valid. So I didn't do that stuff here so that I could fit the whole thing on the screen, but you can imagine how this set name might convert it to some format that we want it to be stored in, and get name might even actually return back something different, might convert it back to what the user originally provided or something like that, so that internally we could use some special representation. And you'll do that kind of thing in some of our activities and some of our homeworks, where the user doesn't have to know that behind the scenes you store something as negative values, but when you hand it back to them, you convert it back to positive values, or whatever the situation is. You can use internal representations that way. Now, the user could still technically access the underscore name and screw it all up, and that's kind of on them at that point. You've written your code so that there's this nice interface that guarantees the right behavior for things. So we saw an example of a constructor before, and how it used this special sort of definition for, or style for defining it, the underscore, and then a name, and then underscore. And there are many of these. So we can override init to create a constructor that's specific to our class. And we can create multiples of these as long as they have different signatures, just like you could do in Java or C++. We could have a default one that takes only self, and then another one that takes self and name, and then another one that takes self and 3 variables, or whatever. Now, the trick to that is, of course, that it's going to be keyed on the number of variables, not the types, because in Python we don't specify the types of those parameters. So if you're worried that you want to have one that's self and a string versus self and an integer, then inside of the function, you will need to check whether the second parameter that they provided you was a string or an integer. So the number of parameters can vary between these, but you're not going to be able to detect the type until you get inside of there and you can actually dig into the variable, the parameter that was passed in, and see what it is. So this is a pretty simple one. It will take self and name. Here, that just means capital A, parentheses, and then the string Sophia. And now we will have created one that has Sophia stored as the instance variable name. There are many others of these, and you will define some of these for one of your projects or more of your projects potentially. There's contains, which allows us to use the keyword in. We can do tests like if the number 3 is in a list, we can say 3 in L, if L is the name of a list. That is calling to the special underscore contains function that's defined for lists, and we can define our own contains. We can define an equality to override double equals, because the default for double equals, as in many languages, is to check memory equality. But if we wanted to only check the user's name being the same as another user's name or that kind of thing, then we could override underscore EQ, and that will give us a new equality measurement. We do, however, just like we did in Java, want to keep the same guarantees between hash, equality, and if we're doing less than or equal to, or greater than or equal to, or different things like that, we want to make sure that those all make sense together, right? If something is not greater than and not less than, then equal had better return true for us. And similarly, if two things are equal, they ought to return the same hash, and all of those. So if you override one and you think there's any chance at all that the others might be used, then you should probably override them too. With less than or equal to, less than, greater than, etc., those won't be defined by default the way that equality will. And so look into which ones are defaults, and you only really have to replace the ones that you think you're going to use. But when you replace one of the less thans, for instance, then you should make sure that there's parity between them, that they all logically make sense as a system. We can make instances of a class be callable like a function by defining underscore call for them. So for instance, here we say that if we call my A class, it's going to print whether or not its name is equal to the parameter name that was provided there. So we created an A, its name variable stores Sophia, and then I call little a parentheses not Sophia as a string, and that will print out false because that's what the call function here says to do. So this is useful if you want to be able to create these sorts of things where the object can also be called like a function and can be used that way. And there are many, many of these built-in special functions with the underscores that you can define to do different things, like a string representation, which you'll have to do at some points. That will be underscore underscore REPR, and it's like a toString. It returns a string representation of your object, and it's what will get called automatically if you ask to print one of your object. If you don't define that, then it's going to use the built-in methods for turning objects into some kind of string representation, probably not the one that you wanted. I want to make special note of the hash function, which gets automatically called when an object needs to be hashed, such as putting it into a dictionary, because dictionaries will hash their keys to be able to store efficiently the values and to look up efficiently the values. So it's best if we override hash to only use immutable parts of our object when hashing, or otherwise prevent the hash somehow from changing. We want to avoid things like what I'm showing here. If I create a person class and then I allow the person's name to change, but I base the hash function on the name, you see here I'm hashing the string because strings have a built-in hash function themselves, that seems valid except for the fact that if the name changes after the person has been stored as a key. So for instance, here we're mapping people's names to alternate stage names, right? So we've created a person called David Jones, and we've said, well, his stage name is Ziggy Stardust. Then the person changes their name to David Bowie. And if we ask, is P equal to the 0th element from the keys of that musician's dictionary? Yes, it is equal because it is actually the exact same object as what was used as the key there, right? P is still the same object as P because I used P, so it will store the same reference. And that's what double equals is checking here because I didn't override underscore EQ for equality. I could ask, is the hash of P equal to the hash of that key from the musician's dictionary? It is because we're rehashing here. But the dictionary, when I said to map P to Ziggy Stardust, meaning map the person David Jones to Ziggy Stardust, it hashed David Jones, which means that whatever number and index David Jones hashed us to is where Ziggy Stardust got stored. But I can pretty well guarantee you that David Bowie is going to hash to a different index and will show up as a different hash value than David Jones. And so now, if I ask, is P in musicians, it will hash David Bowie, because that's what the hash function says to do, is take whatever their current name is and hash it. It will hash David Bowie, get some index that is not the index that the hash for David Jones led us to, and it will say, no, the thing that has that hash value, the one you got from David Bowie, is not in musicians. If I had said to look up a different person that had David Jones as their name, then this would work. I could say, like, new person David Jones, or well, I don't have to say new. I could say person David Jones in musicians. That would come back true because it hashed on this name that was originally given. So the better way to use hashing is to only hash on something that I know will not be able to change. So I should not have written a name change variable or a function. I should not have allowed the names to change for this person class, or I should somehow, for instance, store what the original name was, and that will just forever be their hash, or something like that. Or store what the hash was the first time I did it, and then the hash would always stay the same. Anything like that can be done, but what I should not allow to do is for the hash to come out with a later value or a different value later than it did when the thing was stored. So overall, we're seeing that Python classes are very flexible. We can easily define pieces of them. We can define the instance variables simply by saying self.something and setting a value for it. We can define functions to be non-static by providing them the self parameter, or static by simply not providing them a self parameter. And we can override a lot of the different types of operators and behaviors by using these underscore function names that are special named and get automatically called in different situations, such as init being called when a constructor call is done, or hash being called when something is added to a dictionary. But because we have so much power and so much flexibility with these different functions and these different ways of defining parts of a class, we have to be responsible for using them in ways that make certain guarantees we might want to be true. For example, equality and hashing having a parity to them, much like we discussed in Java. But also for hashing to be done in a way that is consistent. The same object always gives us the same hash value because we don't want to lose it in a dictionary where we've stored it. And similar for our instance variables, we need to make sure that they are defined before we go to use them, because there is no compiler to make sure that self.name exists. There is only the runtime, and the last thing that you want to happen is for your code to get sent out to users, and then the users try to run it, and at runtime, they discover that you've used a variable that wasn't always guaranteed to be defined, or different things like that. And we'll dig more into variable definitions here in the near future, but for now, I hope you get a little bit of a feel for, and that you get a chance to do some work with defining classes in Python and making them have functionality that works for you, but also that has some amount of guarantees and some amount of safeness in this wilder world of free-floating function definitions and class definitions in Python.